Okay, thanks for having me. So this is part one of a series of 2 talks. Today will be completely expository and boring to Paul and most other people here. And it's going to be about explaining homological mirror symmetry for the pair of pants in one of the 2 directions. And so this is after joint work with Mohammed Abu Zaid and Alexander Efimov, Ludmil Kadzarkov, and Dmitry Orlov. And this is not like cutting edge, okay? This is from a few years ago, but I want to use it to both reintroduce or introduce you to wrapped Fukaya categories and the statement of homological mirror symmetry for open manifolds. And then on Friday, I will go wild instead and have a talk with no theorems and only conjectures about extensions of this picture to more generally affine hypersurfaces. So, statement of homological mirror symmetry in general relates the Fukaya category of some symplectic manifold with some category of coherent sheaves on a mirror. Okay? And so the theme here is to look at the case where we do symplectic geometry on the pair of pants, which I will draw like this, which you can think of as, say, P1 minus 3 points, but with a symplectic structure that's making it having cylindrical, infinite cylindrical ends, and the mirror is going to be, well, question mark for now, but it will be revealed in due time. And so first we need to discuss what's something called the wrapped Fukaya category of X. And I suspect about half of the audience is about to take a 15-minute nap. I'm sorry about that, but sorry, turn on more lights. Yes, I can try to. This turns off. I think the lights are on, apart from this one, which is broken. Okay, so the general setup, right, is we want to talk about the wrapped Fukaya category of a Liouville manifold which means essentially an exact symplectic manifold which is convex at infinity. So looks like the symplectization of a contact boundary at infinity. Okay, so X looks like traditional notation after Abu Zaid and Seidel, who introduced this thing, is that you have an inside part, which is an exact symplectic manifold with contact boundary, and at infinity, you have something that looks like contact manifold times an infinite, well, 1 to infinity, with, so the symplectic is d of some one form theta, and now this one here, sorry, theta is contact on boundary of X, and here omega is d of r times, whoops, so alpha, which is, okay, that's the general geometry. And so, okay, so what's the picture that you should have in mind? Well, just that you have some inside part, which is exact symplectic. You have a contact boundary. And then this looks like the positive part of a symplectization of your contact boundary. And in particular, this carries 2 interesting vector fields. One is the Liouville vector field, Z, which is dual to the Liouville form theta, which is conformally expanding. Okay, so it's something that goes just in the cylindrical end, goes radially. You can check that it's basically RDDR in the cylindrical end. And the other one is the Rabe vector field of the contact structure. Which pushes things along the contact boundary. And a natural way to scale it in a symplectization is to make it grow linearly with R. And that's obtained by just taking the Hamiltonian vector field of a quadratic Hamiltonian, which is R squared. Okay? So, okay, so that's the general stage. Yes.
So the first thing is the definition of Z.
Yes, yes.
And then the second thing is a constant follows.
It's a consequence of a local model, yeah.
Oh, but this isn't just true at infinity, this jump, or is it only, where does the electric field live? Everywhere?
It lives everywhere because the symplectic form is globally exact and you've chosen a Liouville form. And so by definition, you can always find a vector field which is dual to the form.
Yeah.
Okay, but at infinity, it will be radial. Inside, it does whatever it must do. Okay? And the Rabe vector field, on the other hand, is, well, I mean, by definition, you take a, inside it's not defined. And what you do is you can take a Hamiltonian which grows quadratically with the radial coordinate and just take the Hamiltonian vector field generated by this. It will spin along each contact slice. Okay, so the Wrap-Fukaya category of a Liouville manifold looks at Lagrangians. Actually, for technical reasons, you could say exact Lagrangians, which are cylindrical at infinity. So the objects of the wrapped category of X are Lagrangian submanifolds let's say exact properly embedded which are conical at infinity. So an exact Lagrangian, if you must know, means theta restricted to the Lagrangian needs to be not just closed, but actually exact, and you require that actually the primitive be compactly supported. Conical at infinity means that in the cylindrical end, L looks like the product of a Legendrian in the contact boundary with the radial direction. So the example today will be in dimension 1. We'll have some Riemann surface, which will be just the pair of pants. The contact boundary will be a union of 3 circles. And we'll just look at things that go straight out to infinity in wherever we go. Okay? Yeah? No. Okay. Okay. So now the question is, what's going to happen? So you want to define Floer theory, Lagrangian Floer theory for such Lagrangians. Okay. Well, as usual, plus extra data like grading data, stuff needed for orientations, and so on. Okay. And so the question is, how do you do the intersection theory of 2 such Lagrangians? And of course, the non-trivial part is, how do you deal with intersections? Well, or lack of intersections, or what's the behavior at infinity of your intersection theory? Okay, so there's 2 general things you could do. One is ask that your Lagrangians go to infinity in specific directions, and then you push just a little bit, or you require them to go to infinity in different directions, and you don't perturb. This would give something that's sometimes called unwrapped, infinitesimally wrapped, or other names, and that's not what we are going to look at today. And the other one is called wrapped because instead you take the viewpoint that you will push things around as much as needed to make all the intersections you might want to see appear. Okay? So specifically, we define the wrapped Floer complex of a pair of Lagrangians to be generated to be a free K module where K is some coefficient field. You could take just complex numbers for today, generated by the intersections, by the time one trajectories of a quadratic Hamiltonian from L0 to L1. So what does this mean? Well, if I have two such Lagrangians, L0 and L1, no, this is maybe L0, this one is maybe L1. I think I've lost the colors anyway. Okay, so I can look at intersection points in the interior. Imagine that your Hamiltonian is very small in the interior, then you just wiggle things a tiny bit. Intersection points will be part of a story of Floer homology as usual. But you also want to look at how the rape flow will take points of L0 to points of L1. So of course, if you don't set any amount of time, you see that L0 will hit L1 in a lot of places here. But instead, we want time one flow. And time one flow for a quadratic Hamiltonian means that we normalize the rape flow by a factor of r. So in fact, a time one trajectory of h, of xh, for this Hamiltonian will occur at a value of r when there's a time r rape chord from one to the other. So the claim is you will have actually generators that correspond to trajectories from the ends of L0 to the ends of L1. But as you go further and further out, you'll have trajectories that make more and more turns. I'm getting lost, so maybe I should stop at some point. Okay. So an easy way to think about that, but easier than viewing, dynamics. These correspond to intersections of the image of L0 under the time one flow with L1. So instead of a picture up there, I would redraw it as, well, I keep L1 unchanged. Oops. But I take the image of L0 by the time one flow, which will still do the same thing in here, but then we'll start spinning in the positive direction along the rape flow in the cylindrical end. Okay, and now these intersections, now we see intersections. See, this intersection came from bending, well, I guess the one chord I didn't draw, this chord here. Okay, and that intersection came from this chord, and so on for the next ones. Okay, so these complexes are usually infinite rank. And this is something that's desirable in mirror symmetry for open manifolds, because if you think about it, well, Lagrangian Floer complexes give morphisms in Fukaya categories. They're supposed to match with, say, morphisms of sheaves on the mirror. And so things like global holomorphic functions should be part of this business. If we're doing mirror symmetry in a non-compact setting, well, spaces of holomorphic functions tend to be infinite dimensional. And you can ask, what's this thing of rotating more and more and more? Well, the best analogy under mirror symmetry is it's like you look at algebraic functions or analytic functions on the mirror whose growth rate is allowed to get larger and larger and larger. Okay, so we are going to see that actually happen when we do an example, that the more terms we put in, the higher the degree of the polynomials that we look at on the mirror. And so to get all polynomials, you need to just allow higher and higher degrees, and that's what happens. Okay. All right. So there's a Floer differential on these kinds of complexes, which can be defined by counting solutions of Floer's equation. So you can either say, well, there's two perspectives depending on how you want to think about this thing. So the actual definition, you look at holomorphic maps from a strip, R times 0, 1, to the manifold X, where one boundary goes to L0, one boundary goes to L1. Let's call the coordinates S and T. And then we want to solve the equation du ds plus j for some choice of almost complex structure on X of du dt minus the Hamiltonian vector field of H equals 0. Okay, so this is a perturbed holomorphic curve equation. And you can see that finite energy solutions want to converge exactly, well, to things that are translation invariant in the S direction. And that means du dt equals xh. So this wants to converge to time 1 trajectories of xh, which are exactly our generators. Okay. So you want to count index 1 solutions to this asymptotic to given time 1 trajectories, and the number of such things will give you the coefficient of d of some generator in d of some other generator. Okay. So if I have here a chord x plus, here a chord x minus, count of these with u of st converging to x plus minus of t at s going to plus minus infinity gives the coefficient of x minus in the boundary of x plus. Sorry. Okay, so the convention we use is the input is on the right, the output is on the left. Okay, Sean seems very puzzled.
That's just the problem with Sean.
Okay, are we okay mostly? Yeah, okay. All right. Now, if you prefer to think of intersections not as chords but as this kind of perturbed picture, then you can also do that. So there's a trick, which is that you can consider instead the map v of s comma t equals the time 1 minus t flow of u of st. And what you find is that this solves, so this is also a map from the strip to x. The equation it solves, well, having put the flow in here compensates for this Hamiltonian term. And so now it solves an equation which is dv ds plus, so now there's a trick about the j, which is, well, it's not the old j anymore, it's j transported by the flow. So it's a t-dependent complex structure. But if you ignore this subtlety, this is really a holomorphic curve equation. Okay? So this is a holomorphic strip for a modified j with boundary on, now, well, at t equals 0, I've applied phi1, so this is on phi1 of L0, and the other boundary is just on L1. Okay. So that means you can now think of this picture where L0 has been pushed. Sorry, I forgot to label it. This is phi1 of L0. And I just want to look for holomorphic strips, of which I think there are none in this picture, so this is a bad illustration. Okay. So there are also product operations and higher products, because this is an A infinity category. So there's compositions. Sorry, so maybe I should have said the Floer complexes give the morphism spaces in the Fukaya category. Okay? And so the composition operations, there will be k-fold products. Okay? And if you know how to define degree gradings, then this should be of degree 2 minus k. If you don't know how to define degrees, then this is useless. And what this one counts is perturbed holomorphic polygons so things whose image there's a boundary on L0, L1, L2, and so on up to Lk, and the ends are asymptotic to trajectories of the Hamiltonian at each of the inputs. Time 1 chords, and well, if you do this, then you have a technical problem, which is that the output of this operation, for technical reasons, wants to be a time k chord of your Hamiltonian. And that's because when you define these kinds of Floer equations, so you might want to draw the domain as being something that's like having several strip-like ends, and then you want to look again at this equation du ds plus j du dt minus xh equals 0. The problem is the t coordinate has to choose a width in consistent manner, and so if you make this input of width 1 and this input is of width 1, then this output wants to be of width 2. And there's no well-defined continuation map from the perturbation given by xh and that given, x2h, so time 2 chords of h, back to xh, time 1 chords of h. There's none unless you're Mohammed and you're really smart. And Mohammed is smart enough to realize that, in fact, the time k, so at the output, what you should expect is k times your given Hamiltonian. And you don't like that. So what Mohammed realizes is that, in fact, the rescaling flow by the Liouville vector field. What? It was you? Oh, sorry. Okay, sorry. Okay, so Paul told Mohammed, and Mohammed wrote it, and everybody thought Mohammed was really smart. He still is, but he is really smart. But okay, sorry. So anyway, so the trick, due to both guys then, is that if you try to recast things in terms of intersections, you have a time k flow coming at the output, but the time log k flow of a Liouville vector field, the one that squishes in the fibers, intertwines the time k flow and the time 1 flow of h. And so you can use that to correct for this issue and land actually in the expected Floer complex with just perturbation h and not k times h. Of course, you have to do that carefully so that it's consistent with the A infinity equations, which I have no time to explain at this point.
That's why the A infinity structure is there, because of the rescaling, because then things are not as
No. The A infinity structure would be here even without these Hamiltonians. It's there in any case because basically, okay, so maybe I should point out for people who are not within this field, the A infinity equations are there in general for, well, several reasons. But one is, if you want to look at why mu2 is not associative on the nose, the answer is mu2 of mu2 counts pairs of holomorphic curves which kind of look like that. You're going to multiply 2 input chords and multiply again by another one and get an output. And the other product, if you compare the associativity, would look like instead you multiply first those 2. So you count pairs again of holomorphic curves or perturbed holomorphic curves that look like that. And you want to say these counts look like they're the same. And why are they the same? Because there should be a cobordism between them, which consists of configurations that look like that. Okay? But now you should think that the domain of this map is biholomorphic to a disk with 4 marked points on its boundary, 3 inputs, 1 output. And the moduli space of these domains is an interval whose endpoints are these 2 things. So everything looks very happy until you realize that actually the moduli space of maps whose domains look like that has extra ends. Okay? These extra ends are things that consist of an operation like that together with a strip, the kind of thing that counts the Floer differential. So you could have actually part of your solution that escapes into the end. Okay? And so this will be the differential. And the count of isolated solutions to this, as you let the domain vary, is what defines exactly mu3. Okay? So that tells you that mu3 defines the homotopy for the failure of mu2 to be associative at chain level. And this is kind of independent of rescaling issues, but now if you bring in rescalings between the inputs and the outputs, you have to do it consistently with this whole story. Okay? All right. So the last thing I wanted to say is how to think of these multiplication pictures concretely in the picture that I just erased, where you push things around. You can think of say, for example, mu2 as, well, you fix so again, this is by the same trick. By considering the map V of st equals some time flow, now it will be 2 minus t of u of st. When you've set up your coordinates the right way, s and t, basically you want the domain to look like that. So that will be something that has boundary on phi squared of L0, the time 2 image of L0, the time 1 image of L1, and just L2. Okay? And so the easiest to explain is now what happens here. Well, for the second input, we had boundaries on L1 and L2, and a time 1 trajectory between them, but we've pushed L1 by time 1, and now we get an intersection point. So our generator, indeed, is an intersection point of phi1 L1 with L2. This is how we recast the notion of chords. Now, instead, the first input, we have flowed L1 by time 1. And so to preserve this idea that we turn time 1 chords into intersections, we need to flow L0 by time 2. So this will be an intersection point of phi1 of L1 with phi time 2 flow of L0. And I can think of that as the image under the time 1 flow of an intersection of phi of L0 with L1. Okay? And now this one is the weirder one. It's an intersection of phi squared L0 with L2. And it corresponds under rescaling of the R variable. So if you want rescaling by flow of a Liouville vector field, it should correspond to some generator x02 in phi1 of L0 with L2. Okay? And time 1 versus time 2 is again corrected for by stretching the radial direction. So let's see this in action, because this is completely incomprehensible as a definition until you actually try to compute. So instead of wondering more about what's the nature of these products, let's do an example. Whoops. First, as a warm-up example, let's do the cylinder. And then we'll do the pair of pants, which is the one I want to focus on. So, and all the pictures I'm going to draw using this trick of pushing the Lagrangians around, you could instead do it without doing that thinking of perturbed holomorphic curves, but the pictures become impossible to visualize. So that's why I'm not going to do it. Probably need a bigger cylinder. I want a really big cylinder. Okay, so let's say that X is the cylinder, R times S1, or if you prefer, P1 minus 2 points, also known as C star. And I want to look at the wrapped Floer cohomology of a Lagrangian I will call L0, which is just R times a point. Or if you prefer, I can think of it as R plus inside this punctured P1. Okay? So what I've said about finding the generators of a Floer complex is I need to look at time 1 chords from L0 to itself, or if you prefer, intersections of L0 with its time 1 image. So let's take the time 1 image of L0, and let's say it looks something like that. Okay. And what do I see? Well, I see that the wrapped Floer complex of L0 with itself has a basis given by intersection points that I will call xi, which I can label conveniently by integers. Okay, so I will call x0 the generator in the middle, which you should think of as corresponding to the minimum of your Hamiltonian. Right? You have a Hamiltonian that grows quadratically with the real variable. Turns out that you can really think of this as r and this as the angle direction. And so there's a minimum in the middle, and then there's further time 1 trajectories each time the derivative hits an integer. Maybe I should say explicitly what is, so if h is r squared, and the symplectic form is d of r d theta, also known as dr d theta, then the Hamiltonian, sorry, I should probably use 1/2 r squared just for simplicity. The Hamiltonian vector field corresponding to this will be r d d theta, which means that if you take theta to have length 1, that's kind of easier to work with, then all the integer values of r are the places where the flow will, in time 1, come back. Right? So this is at r equals 0. At r equals 1, you've actually done one turn in time 1. Let's call this generator x1. And similarly, I can call this one x minus 1, x minus 2, and so on. So I have generators that are indexed by integers. And now I can ask, what is the Floer differential? So the Floer differential would look for holomorphic strips between two such intersection points. And you can see quickly there are none. Actually, if you know your gradings, you know that the natural thing to do is to give all of these guys degree 0, which should tell you that there's no differential. But you can look for also holomorphic strips in here and see that there's none. So now what will be interesting is the product structure. So the product structure, I've said I need 3 copies of my Lagrangian. So let's put a third one. So now I should probably label them. So this is phi1 L0. And the next one will be phi squared. So if I spin twice as fast, then I come back twice as often to the same position. I turn twice as fast. Okay. So this is phi squared of L0. And now I want to look for triangles with given corners, as per this picture. So if I try to understand, for example, it's probably better for me to first see what I want to do and then do it. So let's say I want to multiply x minus 2 with x1. So what I need to do is look at the point x1 as an intersection of, no, because of the usual notations, it should be that way. Anyway, it doesn't really matter which one you choose. So I want to look for things which have corners. No, I want to look for triangles with boundaries on L0, phi1. What am I doing? Something wrong with my picture. Right. Anyway, there's going to be phi1 of L0, and there's going to be phi squared of L0. This purple is here. Okay. With corners at, so here I want to have x1, or rather the time 1 image of x1. And my other input here will be x minus 2. And I don't know what this is in advance, but I will look for things like this. And so you can look at the picture, and the answer is there is one such thing. Gosh, I think I aimed a little bit ambitious, but and then it comes back again here and back at the back, and then it has its final corner here, I believe, and it goes all the way to x minus 2. And exercise is convince yourself that there is indeed a triangle with a corner here, and a corner here. Okay, and if it's too painful, then redo it with a smaller one, like x0 with x1 or something. Okay. So now the question is, what is this third corner? Well, this third corner is an intersection of L0 with phi squared of L0. And that one, well, doesn't come with a label so far, but that's because we haven't yet done what we said we would do, which is observe that intersections of L0 with its time 2 image correspond to the intersection with the time 1 image under stretching everything. R goes to 2R. See, if you take the purple thing, it was obtained by spinning more and more, but instead if you stretch horizontally, it looks a lot like the green one. Yes?
I have such a confusion. What is the area between 2x minus, below the 2x minus 1 slash?
Sorry, what is the area?
So if you start at your x minus 2 corner and follow the green curve, it looks like you forgot to hash some stuff.
Yes, I forgot to something here, and then that as well, and yes. Okay, so the boundary of my thing really goes all the way along the green curve from here all the way to there, and back along the purple back to here, and then along orange back to here. Okay, sorry, yeah, it's a mess. I should have taken a smaller one. So anyway, so the observation is now under stretching the radial coordinate by a factor of 2. This point goes here. And that's what tells me that I should think of it as x minus 1 as a generator of my complex. Okay? Now, this is the only such triangle. And OK, there's orientation issues. You have to decide whether it's a plus or a minus. I'm deciding plus for you. So this tells you the product of x minus 2 and x1 is x minus 1. And you can repeat similarly for any pair of generators. It's exactly the same picture. And it's easiest to convince yourself if you pass to the universal cover, where you'll see a picture like this, that if you have any two inputs, then there will be a unique triangle and it will be determined by the inputs, and in fact will be halfway in between them, which tells you that multiplying xi by xj will give you xi plus j. That's the general rule. Okay? So now you could ask next about higher products. And one option would be to draw more copies of wrapped copies of L0 and look for convex polygons, and notice that there's none. And the simplest, faster way of seeing that there are none is for grading reasons, because all the generators live in degree 0 and mu k lives in degree 2 minus k. Yes?
So here, when you say triangles, you mean triangles which are sort of holomorphic?
Yes. These are.
So how do you know
So there's a basic principle that no matter what almost complex structure I use on a Riemann surface, and even if it's t-dependent, s-dependent, whatever, the image just satisfies the local open mapping principle. And the Riemann mapping, and basically the Riemann mapping theorem kind of applies in a distorted way or something. So basically there's a general principle that what you're counting is immersed polygonal regions with no branch points and locally convex corners. That's what corresponds to rigid holomorphic disks. Yeah, in general, that would be a harder proposition, but on Riemann surfaces, it's easy. Okay. So let's rename x sub I to x to the I using this multiplicative structure. So I forgot to say. Okay, and then mu k is 0 for k not equal to 2. So rename things like that, and we find that the endomorphisms of L0 in the wrapped Fukaya category is just Laurent polynomials in one variable. Okay? As algebra or as algebra or as A infinity algebra, it's automatically formal and there's nothing special to do. So now the next statement is that L0 split generates, or actually in this case generates, the wrapped Fukaya category of the cylinder. What this means is every other Lagrangian you can think of, well, here there's not too many, there's basically just circles that go around, can be expressed as a direct summand in an iterated mapping cone built from copies of L0. And so what that means, so let's call this algebra A. What this means is, in fact, that the wrapped Fukaya category of the cylinder corresponds to perfect modules over the algebra A. One way to map things to one way to realize this is if I have a Lagrangian, let's call it T for a test object, I can look at the wrapped Floer complex of L0 with T as module, or in general A infinity module, over the endomorphisms of L0. Okay. And so now, time to wake up the algebraic geometers and ask them, hey, what are perfect modules over this? Well, the answer is this is the same thing as coherent sheaves over I said I would use k equals c, so I'm just going to use complex numbers, and then I can say c star. If you don't like that, you can say gm or something like that. Okay? And concretely, the way this worked is that L0 corresponds to the structure sheaf of a mirror. And all the other Lagrangians are O modules. So for example, a good exercise is to understand how do you get to, say, circles on the cylinder. So the symplectic geometer will say, how do I get this in terms of that? Well, the answer is, remember, whenever you have several copies of that, you need to insert wrapping. So in fact, what you will have, after you look at it for long enough, will have things like this inside it. So if I take two copies of L0, but one of them I've kind of started wrapping already, and think of this intersection as being 1, and think of this intersection as being x. Or I used to call them x0 and x1. Then if I do the cone of say 1 plus x, well, maybe I should say L0 mapping to L0 by 1 plus x. There's a general principle that mapping cones correspond to Lagrangian surgeries. So the mapping cone of 1 plus x corresponds to smoothing this intersection and that intersection. And what do I see? Well, I see an S1 and two pieces that are trivial. And so this complex, indeed, corresponds to an S1, a particular one with a particular local system and spin structure, which corresponds to a particular skyscraper sheaf of a point on the mirror. All right. So, questions before we move on to the pair of pants, which was meant to be the topic? No? Okay. So let's look next at the pair of pants. So if we look at now pair of pants, so I will think of it as CP1 minus 0, minus 1 and infinity. Okay? So if you prefer, it's C star with a point minus 1 removed. Why minus? Well, because it's going to be convenient for me. Okay? So how do I think of it? Well, I can draw it like that. Okay? And one thing I can do is I can still start by looking at the same Lagrangian that I just did. Okay? So let's look again at L0, which is R plus in here. And that's why I put the puncture at minus 1 rather than 1, so that I don't have to worry about them hitting each other. So now the question is, what is the wrapped Floer complex of L0 with itself? First as a group and then as an infinity algebra. So, well, for that I need to push L0 again by wrapping. And there's some wrapping going on in this puncture, but L0 will never notice it. Right? So all I need to do is just push L0 around and look for intersections. Hey, look, I still have a collection of generators that I can index by integers. Okay, looks promising. Now what about the product structure? So instead of redoing that picture, I will take this one and I will make a puncture here. Okay? Which means I want to redo this blackboard and I want to ask, well, what triangles, how does this puncture affect the existence of triangles? Well, the answer is the big triangle that I chose isn't there anymore because it's been punctured. Actually, I think it passed through the puncture twice. No, just once. Right? So that is not allowed. So in fact, this product now became 0. So this answer is certainly not correct anymore. On the other hand, if I experiment a bit more, let's say that I want to multiply x0 with x1. So that's a much smaller triangle. X0 with x1 would be this one here. That one experimentally does not pass through that puncture. Okay? So then you can ask which ones pass through the punctures, which ones don't. And so you look at the universal cover and you ask when is the central region inside there. Of course, on the universal, sorry, not the universal cover anymore, just the Z-fold cover obtained by unrolling the cylinder. So you have a series of punctures somewhere around here. And if one of them lands in your triangle, you're toast. The answer is you have one in your triangle if and only if the rightmost and leftmost points live on different sides of this central region. Okay? So the revised multiplication formula so this one would still be x1. So the revised multiplication formula is that mu2 of xi xj is xi plus j if I times j is greater or equal to 0, which means either they have the same sign or one is 0, and 0 if they are instead of opposite signs. Which means you probably shouldn't call them powers of a single variable x anymore. That doesn't sound very wise. But you can still call x, negative ones, sorry, let's call the positive ones x to the I for x equals x1, and for all I equal to 0. And you can call x minus I y to the I for y equals x minus 1. And what you get is that the endomorphisms of L0 now look like polynomials in two variables x and y subject to the relation x times y equals 0. Okay? Which you can think of as a deformation of a previous one. The previous one was x times y equals 1, and you just degenerated the 1 to a 0. All right. And this is again true, well, as algebra or as infinity algebra with no higher multiplication. Again, because everything is in degree 0, or again, by looking for higher polygons and finding none. OK. So now you can ask, well, sorry, yes?
Is there an easy description for x, y minus t?
It's the same as, depends what you mean by t.
T is a new endomorphism. So you have 3 generators and 1 relation x1.
I'm sure there is one, but I'm not going to find it right now. So yeah, I mean, yes, it's the ambient space in which this family of pants lives. It's the C star squared with, anyway. Okay, right. So back to this. So now you can ask, what does this tell us about, does this mean that the mirror is, so let's call this A, or if you prefer, that's the curve xy equals 0 inside the affine plane. Okay? So if you knew that L0 generates the Fukaya category, then you would have such a result, because you would say, well, all Lagrangians can be expressed as perfect modules over the algebra A, and that corresponds to things here, possibly. Well, the answer is, unfortunately, L0 does not generate or split generate the wrapped category of a pair of pants. Yet, the wrapped category of L0, of a pair of pants, does embed into modules over A, just not into perfect modules. So there's something that we don't have really a good understanding, at least I don't have a good understanding of in the symplectic side, which is that L0 does not generate in finite time, but it seems to generate infinitely. And I don't know how to make that precise. But we'll see, we'll get to it indirectly. So this claim that the mirror is just the curve, sorry, yes?
The relation between L0 generate
and this statement of embedding?
Yeah.
Well, so if you know, well, so as it is, the implication is broken, okay? But remember, if you have an object that split generates, then you can just make every object of a wrapped Fukaya category with endomorphisms, some infinity algebra A. You can map into modules over A just by taking every object T to Hom L0T as a module over the endomorphisms of L0. And that's a fully faithful embedding when you have a split generator, and in a few other cases, such as this one. Okay? But normally you would use split generation to say that this is guaranteed to be an embedding, and moreover, the image is exactly perfect modules. And in this case, of course, that fails. The image is larger than perfect modules because the statement that we want to get to is that the wrapped Fukaya category of a pair of pants is equivalent to, so maybe I should say derived equivalent or whatever, to coherent sheaves, derived, of xy equals 0. Okay? And coherent sheaves on this nodal curve are bigger than perfect complexes. Not every coherent sheaf can be expressed in terms of a bounded complex of copies of O. That's failure of smoothness, right? Okay. So,
Do you have some other method besides surgery to generate the circles? Can you generate the circles around the puncture?
the circle around the puncture, yes, you can generate it in terms of L0, but it will not be pretty, right? And no, I'm not sure I want to try to do it directly that way. Okay? There's a simpler thing to do, which is to do the correct thing, which is to look at more objects so that you have generators of your category. So what you can do instead is look at 3 Lagrangians. Okay, and maybe I should draw them. Well, I'll draw them like that anyway, putting just the puncture in the middle here. Have L0, let's call this one L1, and let's call this one L2. Okay? And for future reference for the next talk, observe that these are the components of the real part of my pair of pants. Right? This is 0 to infinity along R plus, and this is the negative real axis. So now I can ask, what are the homs between these various objects in the wrapped Fukaya category? Okay, so I'm not going to redo all the pictures because that's just boring. I will just observe, well, if you do homs, say, between L0 and L1, so you push L0 around in this here and here, and you see one infinite sequence of generators that correspond to this chord and things that go further. Okay? So now I'm just going to tell you what the outcome is. Of the calculation. So we find, okay, so from L0 to itself, we've said we get C bracket xy mod xy. From L0 to L1, let's see, where was x? X was to the right. So from L0 to L1, I get something that looks like a copy of C bracket x times some generator U, which I will maybe call it U01. And I'm using this notation because as a module over this, it's exactly what this suggests. X acts by multiplication in here, while y acts by 0. If you calculate the endomorphisms of L1, well, endomorphisms of L1, this is really the same calculation as for L0, just rotating the picture. So I should get, again, polynomials in 2 variables, but I will use a new name for the intersections that occur near this new puncture, just because, again, I want all the module structures to work well together later on. So this one I will call C bracket xz mod xz. Okay? And in that direction, there's another guy, C bracket x times v10, with a property that u01 v10 equals x, and vice versa. L2, the endomorphisms look again like a polynomial ring, mod product equals 0. I will call the variables y and z. And here I have polynomials in z times v12, polynomials in z times v21, polynomials in y times v02, polynomials in y times u20. Okay, so these things are labeled by polynomials in variables. The variables depend on, correspond to basically the orbits at the punctures. So x is here, y is here, and z is here. And you find that indeed multiplying by polynomials in x, y, or z acts exactly as in the way you expect. So these things are expressed as bimodules over the algebras of endomorphisms of those things in a way suggested by the notation. Okay? Yes?
Some secret reason for using V010 and not just V10?
I could call it U. That's fine. Just I was thinking of V for the ones that go clockwise versus, anyway, front versus back, but doesn't matter. Okay. So if you multiply back and forth the generators along the edges, you get the corresponding variable. Okay, so there's two others like that. And other than that, there's no mu2s that you can see. But there is a mu3. In fact, there are two mu3s, which come from looking at basically this triangle, which has a corner at u01, u12, and u20. These are all inputs because they are positive direction chords. The output would be the identity of L0. So the claim is you can find that mu3 of u01, u12, u20 is identity of L0. Sorry, I reverted my notations from, anyway, in some order, okay, in the order that makes sense. Actually, plus minus doesn't really matter. And similarly for the others. Okay? So these mu3s, what they do is they reflect the fact that in fact L0, L1, and L2 are not independent at all. Namely, so if I write it this way, this expresses the fact that L0 is isomorphic to a mapping cone of U12 from L1 to L2. Geometrically, take L1, take L2, bend them a bit so that U12 becomes an intersection you can see, smooth the corner, and you see you get something that's the same as L0. And of course, you can also do it on the other side, which corresponds to coning instead U21 from L2 to L1, which gives you another exact triangle. So in fact, you have two exact triangles. Okay, so we have two exact triangles. One goes and the other one goes the other way around. Whoops. Okay. And there's a classification lemma for A-infinity structures which tells you that the endomorphism algebra, let's call it, I don't know, A hat because it's bigger than the other one, which is going to be the endomorphisms of L0 plus L1 plus L2 as A-infinity algebra is determined by this. So the statement of the classification lemma is if I see an algebra which looks like just the path algebra, the algebra, I mean, basically, it's just, all these morphisms between any two of these three objects. Maybe I should have stated, if you see a category, an infinity category with three objects, and these morphisms and these compositions suggested by the notation, then its infinity structure is determined up to gauge equivalence by knowing that you have these two exact triangles. If you have that, then there's a unique infinity structure. Sorry, yes?
So, L0 and L1 generate by themselves. So
That's right. So yeah, so any two of the three would generate. You don't need all three, but then if you only take two, then your two triangles become a rectangle, and then instead you have to look at a mu4. You could do that. It's just.
So the reason you keep the symmetry thing is then you can use this off-the-shelf algebra.
Yes, well, yeah. The algebra seems slightly easier, and it seems more natural to keep all three. Okay? So now you can ask, well, does this still fit with what we wanted on the mirror? So the other side, let's look at xy equals 0 in the affine plane. And let's ask, what objects should we associate to these three things? Okay? So I'm going to tell you right away. But let me use the same notations as my notes so that I can be not too confused. So if you prefer, the ring that's happening here is C bracket xy mod xy will be working in the category of R modules. And so there's two interesting modules. One is R mod y, which you can think of as C of x. And the other one is R mod x, which you can think of as C of y. Okay? So in terms of more geometric language, so this is the structure sheaf of this whole thing. But this thing is reducible. It's a union of two components, A and B. So I will call A the x-axis, and I will call B the y-axis, defined by x equals 0. Okay, and that's what they are as modules over that one. And they're not perfect modules, so that's where you see that something was interesting and going on. So now you can ask, well, what are the endomorphisms? What's the endomorphism algebra of these three objects? Okay. So, okay. Yes, that seems to be the right way to place them. I claim this is how they will fit. So endomorphisms of O, that's just the ring of functions. So this is R, which is C bracket xy mod xy. From O to OA, well, it's global sections of OA, which you can think of as just functions on the x-axis. So this is C bracket x as a module over R. Okay? So far, I'm not doing anything. And this is C bracket y as a module over R. So now you can ask, what are the endomorphisms of OA? Okay? So if you just look for Homs, you'll just get polynomials in X. But there are non-trivial X's. So time to showcase my skill at the B-side dark arts. If I want to compute X of OA, okay, which is the same thing as, it's going to be easier to use the ring for notations. So I'm supposed to use a free resolution, well, a projective resolution, and the observation is R mod y has a resolution because it's a quotient of R by the ideal generated by y. What's the kernel of this map? Well, the kernel of multiplication by y is all the things that have an x. It's the ideal generated by x. So I can resolve, the kernel is the image of multiplication by x. Now, what's the kernel of that one? Well, things that die under multiplication by x are things that have a y in them, and so on. Okay? So R mod y has an infinite resolution, which is in fact 2 periodic by copies of R. And now I want to take Hom of this resolution to R mod y. So I apply Hom the R mod y to this resolution. So I get, okay, Hom R mod y is just R mod y. Everywhere. And the connecting maps are just multiplication by y, multiplication by x, multiplication by y, and so on. Okay, so when I look R mod y, well, on R mod y, y acts by 0, right? So these guys are trivial. Let's have a few more, and so on. Okay, so half of the maps become 0. And now remember that R mod y was really secretly x times what do I want to say? No, it's C of x, right? And multiplication by x from C of x to itself is injective, but its co-kernel is the constants. Okay, so you find that in degree 0 you have R mod y. In degree 1 you'll get 0, because this is injective. In degree 2 you'll get a copy of a field, which is just, you know, the kernel of multiplication, the co-kernel, you know, you can think of it as R mod y and x, if you want. Here I'll get 0, and here again I'll get a copy of C, and so on. Okay, so let's give a name to this guy. There's a guy Z in x2 of R mod y, which is this class. Okay, and then this guy, it turns out, is Z squared, and so on. And x, of course, acts trivially on Z. Y acts trivially. So, no, x. Sorry, y has been set to 0. So the statement is this is, in fact, again, a polynomial ring in two variables, x and z, with the relation xz equals 0. For now, degree of z is 2. Now you go back to your other picture because you're a bit worried. And then you realize that if you know something about gradings in Floer theory, you need to choose a trivialization of a tangent bundle to define gradings. And implicitly, if I give degree 0 to the things I saw before, then I chose the trivialization that comes from the usual trivialization on the cylinder. And that trivialization does not look the same near that puncture. And in fact, that's what causes, well, the rotation number of these orbits is 0 in that trivialization, but this one has rotation number 2 in that trivialization. So degree of z equals 2 is completely right. Okay, now you can continue the story. B is handled the same way. You'll find polynomials in y and something else I call z again, just by abuse of notation, which is a class in x2 of R mod x with itself. And then I'll find that these things look like polynomials in z. And these ones, you know, anyway, so there's more calculations to do, all of this flavor. And you find things like that. I should probably put an x here and a y here and a z on one of these. Okay. So this looks like the same algebra. What about the higher products? Well, again, I just need to test that there are, you know, exact triangles. And the statement is indeed there exist two short exact sequences of sheaves and that one, just coming from, you know, inclusion and quotienting, and they give me the desired exact triangles in the derived category, and so I'm perfectly happy. Okay. Okay, so the consequence is now we conclude that, well, this equivalence is true. Okay, the theorem follows. And, well, it's exactly 12, so this is a good place to stop.